One of the coolest parts about this chapter by far are the labs and being able to see what happens with our different electrons when we excite them. Okay, so normally they exist here in the ground state, um, and then when you add energy, they get excited and they jump up really, really high. Okay, they're like so excited. And that's kind of what we're talking about with our photoelectric effect. Okay, so when you see your normal ground state atom right here, where this electron, this photon is just hanging out there, and then it jumps up when it absorbs energy. And then what goes up must come down. So it's then going to release energy in the form of light when it returns to the ground state. And that's where we get these beautiful demos that you see in the lab. We do the flame test lab where this person right here does the flame test for lithium and sodium and magnesium. We're going to mute her. But you can end up seeing here's our Bunsen burner, and then she puts in our different um, elements. This is our lithium, and notice how it's like this fuchsia color. And then you can see she puts in, um, let's see, it's still going to be our lithium. Here we are cleaning our flame, and then we put in sodium and see that it is a yellow flame. And as this buffers a little bit, it goes through and shows you all of those beautiful colors. I like to bring in my mystical fire packets, and you can see you might have used those for your campfires, and you can basically change the colors of all of your flames. Down here is potassium, but this is those electrons jumping up and down from one energy level to another, and it's really quite amazing. So you can focus on all the different colors in the flame there, and that's essentially what fireworks are. You make all those predictable different colors through adding these different metal salts. So very cool demonstrations that we use in class. This video over here uses some ethanol and some different metals in order to make a rainbow flame, and it's just really cool because it's kind of hot at the same time, and I mean you can't forget how lit it is because it's just super cool. But these aren't loading right now. Sometimes with the Screencastify or Screencast-O-Matic, it changes the availability, but I'll link them on my website and on my uh, Google Classroom and stuff. In class, I actually have this poster, the Have You Seen the Light poster, and you can download a Zapper app for it, and these are like screenshots of the whole thing, and basically you look through it through your camera. And it's an augmented reality, and it changes the flames. I got this from my friend who at the University of Cambridge in England, and you can end up seeing the really cool flames and how they move in there. The spectrum is what we are looking at in these labs, that narrow beam of light that's emitted. And then we shine it through a prism, just like Pink Floyd here, and separate it into a spectrum. So this is basically how rainbows are formed, um, with water being the prism, and this is your sunlight, because sunlight is actually a combination of all of the colors. So you see this continuous spectrum over here. It's not just, you know, a great old Philly pastime. So there are two major types of spectra. There are continuous line spectra and emission spectra. The continuous line spectrum is going to be that of sunlight, and that is going to be that continuous range of frequencies. So you see every single shade of red, orange, yellow, green, blue, and violet, and indigo too. Okay, the emission spectrum is going to be for a specific substance because these substances are not going to have all of the electrons that the sunlight will. So if you see an element of calcium, it's going to have a very specific, almost like fingerprint, are what these emissions are going to be. So here you'll see some spectra for lithium. Okay, so like we saw in that previous video, that lithium is going to be that fuchsia color, that really fuchsia, deep red. So to get that specific type of red, it's a little bit of red, a yellow, some greens and purples. Sodium is mainly going to be yellow, which is why you see mainly just yellow here. Neon is going to be like an orangey color, and that's because it's a lot of reds and some oranges, some yellow, and a couple of greens. It's like getting custom paint colors, like at the Home Depot or Lowe's or something. When you get that specific color, they have to add in a little bit of each one of the shades. But potassium here is a violet color, so you'll see that you have some purple, some red, and some of these yellows and greens in between. But these specific, almost like fingerprints, um, are due to the specific electrons jumping and falling back down to their ground state in that photoelectric effect. We use a spectroscope in class, and we look at these different emission spectra as we go through. And this wonderful little scientist here ends up putting a prism in front of different kinds of light, and you can actually see how these things are emitted. And if I can get this to work okay. Um, Oops, I don't want to add more videos for him. Let's go back. Um, but play with these and try to get it to jump ahead, and you can see the actual emission spectra on there, um, and you'll see the different colors of the red and the orange and the yellow and the blue. But again, I will put links to this stuff in my website and Google Classroom for you to see as well. Okay, and the very last thing to know from our chapter is that the hydrogen spectra that we can see, um, there's more to it than what is visible. Okay, so the scientist Balmer looked at the violet light that comes from our hydrogen. It's basically two reds, um, a blue, and a violet that makes that very specific shade of like a violet blue. And it was originally thought to be the only emission. But when you look at it through different lenses, you saw that there was also an ultraviolet radiation series that was emitted. And you could also see that there was some infrared light emitted as well, things that we can't see with our naked eye. So the Lyman series is the ultraviolet, the Passion series is the infrared. And what they found is that if the Balmer series, which is going to be your visible light, is basically when the electrons jump from the fifth and the fourth and the third energy levels back to the second energy levels, whereas the Lyman series, which is going to be your ultraviolet light, is when they fall back down to the ground state. And then the Passion series here, which is the infrared, is going to be when they fall down to the third energy level. So sometimes it bumps up to one, it bumps up to another, and it falls down to different amounts. So it's very interesting how it all comes about. But one way I like to remind kids to do this is to make up a weird word like bivloopy. Okay, so Balmer, visible, Lyman, ultraviolet, Passion, infrared. Or another way that you can do this is that we have a principle Palmer, which is close to a Balmer, and we can see him visibly. Ultraviolet radiation happens when a man lies down and lays out, from the sun. And passion, oh, what is the color of passion? That would be your red color. So that's one of the things that you can do to kind of remember how each one of them all works about. This last website right here is a hydrogen atom simulator, and is one way that you can walk through your atoms and release um, and fire photons at it, and you can see when things are absorbed and whether they are in the visible range or the non-visible range, and you can kind of play with a simulator and see what happens to all these different frequencies, and now you're in the ultraviolet range, which is why you see it be red right there. But you have some really cool little things to play with in our um, chapter. Okay, so ladies and gents, this is the absorption and arrangement of electrons in our atom. I hope you learned something good. If you have any questions, please let me know, and take care.